Hello, everyone. In this video, we're going to look at part B in example 3. So for part B, again, we're given a sequence and we're asked to determine if it converges or diverges. So let's go ahead and set up that limit to determine what happens with this sequence. So we're looking at the limit as n goes to infinity of e to the 2n over 5 e to the n plus 1. So we can see that the behavior of the numerator as n goes to infinity will go to infinity, and the denominator also goes to infinity. So just like the last problems we've seen, we're going to use L'Hopital's rule. So that means this is equal to the limit as n goes to infinity of derivative of that numerator, e 2 to the n, is going to be e 2 to the n, but then we also have that 2, because we're using a chain rule here. We need to include the derivative of that inside 2n function. And then the derivative of the denominator will just be 5 e to the n. That's because that 1 in the denominator derivative will just be a constant, or the 1 is a constant, so the derivative will be 0. Okay, so now we can see that some things cancel out. So what happens? Well, an e to the n cancels with one of the e to the n's in the numerator. So we can kind of take that one more step. So this becomes e to the n times e to the n if we want to split up that 2n. That's because when we have the same base, we add exponents. So that would become e to the 2n. Or if we start with e to the 2n, then we could rewrite that as e to the n times e to the n. So one of those e to the n's will cancel, and we'll still have one remaining. Okay, so what does that mean? That means this becomes the limit as n goes to infinity of 2 e to the n over 5. Now, what happens there? Well, this denominator just stays at a constant 5, no matter what n does. But this numerator blows up into infinity. So when the numerator blows up larger and larger, the denominator stays fixed. That means this entire limit will blow up, will go to infinity. So we can say, so the sequence converges. No, is that the right word? No, diverges. Diverges. Goes to infinity. Okay, but I want to look at an alternate solution here. Alternate solution. Okay. So let's again start with, so what you just saw, what we just worked out through together, was using this L'Hopital's rule to compute the limit. But in this solution, we're not going to use L'Hopital's rule. We're going to use some clever algebra. The reason why we're going to do this is because in some examples or sequences, it's going to be more useful to use the method, this method that I'm about to show you, than it will be to use L'Hopital's rule. And that's in the case when either L'Hopital's rule doesn't apply, maybe we don't have the infinity over infinity form, or maybe the derivatives are too complicated to work out. Okay, but let's go ahead and start with the limit as n goes to infinity of e to the 2n over 5 e to the n plus 1. Okay, so now what we can do at this stage is manipulate this term here to make it a little bit easier to work with. So what we can do here is multiply the numerator and denominator by 1 over e to the n. So why are we doing that? Well, this e to the n on the denominator is kind of giving us issue because we also have like an e to the n type thing in the numerator. So by dividing out 1, or by multiplying 1 over e to the n, that's going to help cancel some of the terms in the denominator. Okay, and we can do this. This is a legitimate move because we're not changing this term here at all, because we're doing the same thing to the numerator and denominator. So we're just multiplying by 1. So we don't change anything about the limit here in the original term. Okay, so this is going to be equal to then the limit as n goes to infinity of e to the 2n over e to the n all over 5 e to the n over e to the n plus 1 over e to the n. So we're just bringing that 1 over e to the n into each term. Okay, so now some things cancel, which is nice. So this e to the n cancels in the denominator. One of the e to the n's here cancels with an e to the n in the numerator. So then we can write this out as the limit as n goes to infinity of e to the n over 5 plus 1 over e to the n. So now let's look at the behavior of each term in this fraction that we've set up. So in the numerator, as n gets larger, this term is just going to go to infinity. So we might think that this was all for nothing. We're still going to infinity in the numerator. But let's pause and look what happens to the denominator. So 5 stays fixed again. 1 over e to the n, well, e to the n blows up, so that fraction 1 over e to the n goes to 0. So that means that entire denominator will just go to a fixed 5, because 5 plus 0 in the end. So again, we're seeing that behavior where the numerator blows up, the denominator is a fixed constant. So here then, this limit will also blow up. So we go to infinity again. And we can write that out in maybe one more step. So maybe before writing infinity, we can write the limit as n goes to infinity. So we're just taking that limit again, e to the n over 5. Again, because this first term here, or this term in the denominator, 1 over e to the n goes to 0. So we can go ahead and take that limit and then look at our fraction from there. And again, similar reasoning, numerator blows up, denominator goes to 0 to 5, a fixed constant that's not 0, because if it does go to 0, some weird things could happen. But here, pretty simple, numerator goes to infinity, denominator goes to 5, so we blow up and go to infinity. Okay, the second alternate solution, you might think, oh, that was so much more complicated. But again, in some situations, this type of algebraic manipulation is actually going to really simplify our sequence and our limit. All right, thank you so much for watching. Keep up the hard work.